My dear student, colleagues and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics Webinar. Today is our 253rd International Physics Webinar. We have with us here today Dr. John Ellis, sir, CBE, FRS, Professor Clerk, Maxwell, Professor of Theoretical Physics, Department of Physics, King's College, London, UK. And he has already connected with us, so I'd like to welcome our speaker. Sir, good evening and good afternoon to your part. And thanks for joining with us, sir. And thanks for accepting our invitation, sir. So before going to you, I'd like to introduce you, though everybody knows you well, shortly. So our speaker, John Ellis, currently holds the Clerk Maxwell Professorship of Theoretical Physics at King's College London. After his 1971 PhD from Cambridge University, he worked as SLAC, Caltech, and CERN Geneva, where he was theory division leaders for 6 years. His research interests focus on the phenomenological aspect of elementary particle physics and its connections with astrophysics, cosmology, and quantum gravity. Much of his work relates directly to interpreting results of searching for new particles. He was one of the first to study how the Higgs boson could be produced and discovered. He is currently very active in efforts to understand the Higgs particles discovered recently at CERN, as well as its implication for possible new physics such as dark matter and supersymmetry. He also studies possible future particle accelerators such as compact linear collider, CLIC, and future circular colliders. Is known for his relentless efforts to promote global collaboration in particle physics. John Ellis was awarded the Maxwell Medal in 1982 and Paul Dirac Prize in 2005 by the Institute of Physics. He was elected Fellow of the Royal Society of London in 1985 and the Institute of Physics in 1991. I think you will enjoy our session, and the title of this today's International Physics webinar is How the Anomalous is the Anomalous Magnetic Moment of the Muon. So, sir, it's your time, sir. You can start. And I think it's a great opportunity for us students and viewers to learn a lot of things about the muon and magnetic moment of muon.
Okay, well, thank you very much for this kind introduction. It's a pleasure for me to be back with you today. So you may have heard that there was quite a lot of excitement in spring of 2021 when there was a new experimental result from Fermilab in the United States. What they did was they measured the magnetic properties of the muon particle, and they discovered it did not behave according to calculations in the standard model. So this then raises the question whether this quantity, the anomalous magnetic moment of the muon, may be a portal towards new physics beyond the standard model. And that's the topic that I want to discuss today. So this image here, which I took from a Fermilab website, gives you some idea of the microscopic examination of the muon and its properties, which is underway at the moment. And in particular, as I'll discuss later in this talk, there's this mysterious blob shaped like an egg in the middle of the picture, which is the subject of much discussion at the moment. So this is an image of Fermilab. And what you see here is a truck bringing to Fermilab the magnet which is used for this experiment on the magnetic properties of the muon. Now, this is just the latest in a long series of experiments. I count 8 experiments, and many theorists have also worked on the properties of the muon. And it's a story which I'm going to take back to 1927, as I'm going to discuss in a moment. But before discussing the magnetic properties of the muon, I should actually introduce the muon to you. So, as you know, the Earth is bathed in cosmic rays, energetic particles, coming from big explosions elsewhere in the universe. So these were discovered a bit over a century ago by Victor Hess, whom you see in the left picture here. So he went up underneath a balloon and he discovered that there were these showers of particles coming down from the cosmic rays striking the upper atmosphere. So what happens is that the energy of the primary cosmic ray is then converted, according to Einstein's E equal to mc squared, into the masses of many other particles, potentially heavy particles, some lighter particles. And in fact, in the first half of the last century, many previously unknown types of particle were discovered by looking at these showers produced by the cosmic rays. And one of them was the muon. So it was discovered in 1936 by Carl Anderson, who had previously discovered the positron, the antiparticle of the electron, and Seth Neddermeyer. So what they did was they looked what happened to the particles produced by cosmic rays as they passed through a magnetic field. So any charged particle will be bent in a magnetic field. Protons are bent, electrons are bent. And the amount by which they are bent depends on their mass. So, for example, the electron has a relatively small mass, but it has the same magnitude of electric charge as the proton. So the electron is bent quite sharply, and the proton is less bent. Now, what Anderson and Neddermeyer discovered were particles that were bent somewhere in between the electron and the proton. And, well, the electron, of course, is negatively charged, the proton is positively charged, but these intermediate particles existed in both positive and negative charged forms. So the difference in the curvature of their tracks indicated that they have mass bigger than that of the electron, but smaller than that of the proton. Now, in those days, Yukawa had predicted that such a particle could exist. And initially, it was thought that maybe the muon might be that particle, the meson, which mediated the interactions between protons and neutrons inside nuclei. But it was quickly discovered that that interpretation of this new particle, the muon, didn't work because the muon did not interact strongly. It only has electromagnetic and weak interactions. So this was a particle that was not predicted. And here you see a picture of the Nobel Prize winner, Rabi, who remarked when he heard of the discovery of the muon, who ordered that? So his idea was it was like you go to a Chinese restaurant and lots of different dishes arrive on the table, but there's one dish on the table that nobody ordered. And that was the way that he regarded the muon. So who ordered that? We still don't know. We still don't know why the muon exists, but it does. So what are its properties? So it has the same electric charge as the electron. It has weak interactions, and detailed studies have shown that the weak interactions of the muon and the electron are the same. But it weighs 200 times more. We have no idea why it weighs 200 times more, but that's the way it is. So the lifetime of the muon has been measured quite accurately, initially with cosmic rays and now at accelerators, and it's about a microsecond. So this means that if you produce a muon in the upper atmosphere from the collision of a cosmic ray, then although its lifetime is very short, if it's produced with high energy, then relativistic time dilation means that the muon can survive and reach us at ground level, or even below. And the flux of cosmic rays at the Earth's surface is about 1 per square meter per second. And something like 80% of those charged particles that hit the Earth's surface are actually muons. Now, the more energetic muons continue. Remember, they don't have strong interactions, and they can penetrate kilometers of rock. And this picture, which you see here, is taken from a paper by a Chinese laboratory. And as you can see here, they measured cosmic ray muons at a depth of almost 7 kilometers equivalent water depth. So muons, they weigh more than the electron, and they're very penetrating particles. So that the muons passing through us as I speak and you listen. So where does the muon fit in the standard model of elementary particles? So I talked about the standard model previously in this lecture series, and you'll remember that in the standard model you have matter particles, so the quarks on the left, and on the right the particles called leptons that don't have the strong interactions. And the first example, of course, was the electron, and the muon looks just like the electron, except that it's heavier. And subsequently, a third very similar type of particle, the tau, was also discovered. So 3 of them, we don't know why they're 3. We don't know why they have the masses that they do. So we distinguish in the standard model 4 fundamental interactions. There's gravity, electromagnetism, and the strong and weak nuclear force. So the muon is very penetrating. It doesn't have the strong nuclear force. It has an electric charge, and it also has the weak interactions. So that's how the muon sits inside the standard model. Now, I'm going to be talking about the anomalous magnetic moment of the muon. But first, I better describe how it is that an elementary particle can act like a magnet. So I remind you that if you have a current running in a solenoid, as illustrated in this picture here, then it produces a magnetic field in much the same way as a bar magnet. So you can imagine in this picture that there is one pole of the magnet at this end and the other pole at the other end. And depending on how much electric current you have flowing around this loop, then you get a larger or smaller magnetic field generated. Now, let's consider a charged particle. Now, charged particles can spin. The electron spins. It has a half a unit of angular momentum, so it's quite a small spin, but nevertheless, the electron is spinning. And it has a charge. Now, if all that charge were concentrated in the middle, then as it rotates, it will not generate a magnetic field. But suppose that the charge distribution is spread out. Then, as the electron rotates, it's like an electric current going around a solenoid, and so you can generate a magnetic field. And in that way, an elementary particle like the electron or like the muon can have a magnetic moment. So this was first calculated by Dirac in his fundamental paper on the quantum theory of the electron in 1928. So many of you, I'm sure, are familiar with the famous Dirac equation that he wrote down. And here on this slide, I've written it the way we write it nowadays. In a moment, you'll see how he wrote it, but it's the same equation. And Dirac discovered something that surprised him very much, that this equation actually predicted that the electron would have a magnetic moment equal to 2 in dimensionless units. And he wrote that this was really an unexpected bonus for me, completely unexpected. So magnetic moment of 2, that will be a canonical magnetic moment. But my title talks about an anomalous magnetic moment. So what does that mean? So we have to go back to another paper by Dirac in 1927, quantum theory of the emission and absorption of radiation. So he basically, in that paper, laid out the basis for the quantum version of electrodynamics, QED. And in that theory, you can calculate quantum corrections to the electron's magnetic moment or the muon's magnetic moment. And you find that the magnetic moment is no longer equal to 2, and that's the anomaly that we're talking about. So I promised to show you the way that Dirac wrote the equation. And so here it is, outlined in red there. And you can see it's a bit more complicated than the way we write it nowadays, but it's basically the same equation. So using his theory, Dirac's theory, of the quantum emission and absorption of radiation, it was possible to calculate the quantum correction to the magnetic moment of the electron, or the muon. And that calculation was first done by Schwinger, whom you see in this picture here, in 1947. So he was very proud of that calculation, so proud of that equation that he actually put his result on his tombstone. So you can see the first line on the tombstone is the anomalous magnetic moment of the electron that he calculated, alpha over 2 pi, where alpha is the fine structure constant. Then there's him, when he was born and when he died, and in third place comes his wife. Well, you know, if I ever get to write an equation on my tombstone, I can promise you that my wife will appear first, I will appear second, and my formula will be at the bottom. So Schwinger's calculation applies to both the electron and the muon. And the first measurement of the magnetic moment of the muon, what we call G mu minus 2, was made by Lederman and collaborators in 1957. So here's the front page of their paper. And if you look at the equations here, you can see an expression for the magnetic moment, G, which is equal to 2. That's the canonical value. And then there's a first quantum correction, alpha over 2 pi. And then as a higher order quantum correction, alpha over pi squared, with a coefficient of 0.75. So all that means that the magnetic moment of the muon differs from the canonical value of 2 by something like 1 per mil, as you can see at the bottom of the slide. And this first measurement by Lederman and collaborators agreed very well with the calculations by Schwinger and other people. So that was the first experiment on the anomalous magnetic moment of the muon. In fact, there was another experiment which was done shortly afterwards at CERN. And here I show you a couple of pictures of the people who did that experiment. And one of them you maybe recognize, that one here, who was the same as this one over here. That's Georges J-PARC, who, like Leon Lederman, won the Nobel Prize. He didn't win the Nobel Prize for measuring the magnetic moment of the muon, but they got the Nobel Prize nevertheless. So what they did was they built a long magnet. So they had a magnetic field running along there. And then they injected muons, and then the muons spiral around the magnetic field line, the spiraling just being the movement of a charged particle in a magnetic field. But as they go around, their spin precesses, and it precesses by an amount related to the anomalous magnetic moment. And in their experiment, they were able to measure the anomalous magnetic moment with a precision of 0.4%. So in this picture, they're designing their experiment, and in this picture here, they're actually sitting on their magnet, which I think can still be seen at CERN. So subsequently, instead of having these long, straight magnets, people did experiments with storage rings. So this picture here illustrates the principle. So you start off with a beam of protons. You hit a target. The target produces different types of particles, including in particular pions. Pions decay into muons, and when those muons are produced, they're automatically spinning. So then you capture those muons in a storage ring, so it has a magnetic field. The muons go around, and as they go around, the spin axis of the muon precesses. Now, how can you measure that precession in the direction of the muon's spin? So the muon decays into an electron plus neutrinos, and the direction in which the electrons come out depends on the direction of the muon spin. So you put detectors around your storage ring, you measure the electrons, and the way in which the intensity of the electrons varies tells you how rapidly the muon is spinning, and that tells you the anomalous magnetic moment. So this was the first storage ring experiment that was done at CERN in the 1960s. And this experiment measured the anomalous magnetic moment, called here A, with an accuracy of 270 parts per million. So better than 1 part in 1,000. And it agreed with calculations that were done in quantum electrodynamics. Now, I should say, by the way, that in parallel with these new experiments, theorists were working very hard to calculate corrections, quantum corrections to the anomalous magnetic moments of the electron and the muon. So I mention here a couple of the leaders in that field, Kinoshita and Lautrup. And in particular, they pioneered the calculations of 3-loop quantum diagrams. So you see here, well, for example, let's look at this so-called rainbow diagram. So that first loop, that's what gives you the alpha over pi, the 2 pi found by Schwinger. And then there's an alpha over pi quantity squared given by a second loop. And then there's a third loop. So as you can see, these calculations are getting quite complicated. They even went on to calculate the alpha over pi to the 4th terms. And here we see the rainbow diagram, this time now with 4 photons curling around. So they calculated the anomalous magnetic moments of both the electron and the muon, and this here is 8th order contribution. So shortly after they did this, CERN did a second storage ring experiment. So this ring is rather bigger than the first one. And I'd just like to mention a fundamental principle of this experiment and subsequent storage ring experiments. So, as I mentioned, the spin of the muon precesses, and it precesses at a rate that's determined by the anomalous magnetic moment, this quantity A mu. Now, it can precess because of the magnetic field. It could also precess because of an electric field, if there's an electric field. Now, what people did was a very cunning choice of the energy of the muon. if you go to 3.094 GeV, then these two contributions here to the precession and the electric field cancel out. And that means that you only have to worry about the precession in the magnetic field. And moreover, you can get rid of this second term here if you make sure that the magnetic field is perpendicular to the ring. So the precession frequency was directly proportional to the magnetic field given by the anomalous magnetic moment. And here you see some results from the CERN experiment. So as the muon spin precesses, the intensity of the electron varies with a frequency which is given by the anomalous magnetic moment. And they were able to measure that anomalous magnetic moment with an accuracy of 8 parts per million, so better than 1 part in 100,000. Now, so far, all the calculations were in perfect agreement with calculations in QED, what we would now call the standard model. Now, as I discussed in one of my previous lectures, we expect that there should be physics beyond the standard model. And in particular, I've mentioned previously that my favorite extension of the standard model is something called supersymmetry. And there's all sorts of reasons why one might like it. Results from the LHC, for example. It appears in unified theories and string theory. It could provide dark matter. And it could make an important contribution to the anomalous magnetic moment of the muon. So let me just briefly remind you of the particles in the minimal supersymmetric extension of the standard model. So here on the left, we have the standard particles. And here on the right, we have their supersymmetric partners, indicated by these tildes sitting above. So the supersymmetric particles have the same internal properties like electric charge as standard model particles, but they spin in a different way. In particular, the supersymmetric partner of the muon has no spin, whereas the muon has half a unit, just like the electron. Now, within this set of supersymmetric particles, there are candidates for producing the dark matter that fills the universe, something else that I discussed in an earlier lecture. So if they are relatively light, and if also the muon's partner, the muon, is also relatively light, then you can get an important contribution to the anomalous magnetic moment of the muon. Over the years, many people have calculated this supersymmetric contribution to the anomalous magnetic moment of the muon. In particular, I've been involved in various calculations of that, the first one being back in 1982. So if you can make out these little diagrams here, these are the diagrams that we calculated. And if you look at them, you can sort of imagine that these diagrams would cause the charge distribution of the muon to spread out. And I remind you that the magnetic moment is related rather like the electric current in a solenoid. And if you spread the charge distribution out, and if the muon is rotating, that gives you an electric current, which depends on how far spread out the muon charge distribution is. So supersymmetric particles can affect that charge distribution, and they can affect the anomalous magnetic moment of the muon. So that was in 1982. So over the following 20 years, there was an experiment done at the Brookhaven Laboratory in the United States using a storage ring, like the CERN experiment, to measure the anomalous magnetic moment of the muon. And here is the experimental team, at least the leaders of the experimental team. And so this guy here also won the Nobel Prize, but again, not for this experiment. So what did they find? So they measured the anomalous magnetic moments of both positive and negatively charged muons, and this is the average. And over here in blue, we have theoretical calculations. Now, those theoretical calculations were not done on the basis of first principle. They were done using experimental data. If you remember, on my first slide, I had a sort of egg-shaped blob in the center of the picture. And one of the most difficult parts of the theory is to calculate the contribution of that blob. And for that, you can use electron-positron annihilation data, as I'll discuss in a moment. And this is the result if you use those data. And it looks like it may not agree very well with the theory. So here's the theory, here's the experimental value, here's the theory. Looks like there may be some difference. So I did another calculation of that about 20 years ago, and we showed, other people did the same thing, that if there are supersymmetric particles weighing a few hundred GeV, then they could make a contribution to the anomalous magnetic moment of the muon, which could explain that discrepancy seen in the Brookhaven experiment. Meanwhile, other theorists were doing more calculations in quantum electrodynamics, quantum QED, quantum electrodynamics. In particular, Kinoshita, who is really one of the world leaders in this business, he's been in it for probably 50 years by now. And here we got yet another rainbow diagram, this time with 5 photons going around. So in 2020, a very large group of theorists got together and reviewed all the theoretical calculations. And they reviewed not just the calculations, but also gave a very careful discussion of the uncertainties in the calculations, particularly in the calculation of that egg-shaped blob that I had on my first slide. So here's another representation of that blob. It's no longer quite egg-shaped, it's kind of circular. It's no longer yellowish, it's gray, but it's the same blob. Now, the point to be made here is that if you cut that blob in half, then you get what looks like this piece of the Feynman diagram here. And that's the leading diagram for electron and positron annihilating to produce hadronic particles, pions, mesons, or so if you go to high enough energies, protons and the like. So you can calculate this blob, this egg, if you measure the way in which the photon produces strongly interacting particles, hadrons. So I'm not going to go through the details of this calculation, which are very complicated. You need the data from many different experiments over a wide range of energies. And as you can see, the data are quite precise. They don't always agree terribly well, but good enough, it seems, to confront the theory. So the most important contribution comes from relatively low energies, and that's also contributes very importantly to the uncertainty in the calculation. So what happens when you do this? So these are the results of these calculations using electron-positron annihilation data. And over here, we have the result from the Brookhaven experiment. And as you can see, there's quite a significant discrepancy. I should mention that in addition to these calculations, which use data to calculate that blob, There are also people who use the lattice, so a discrete version of space-time, to do a first principles calculation, but most of those results are not very accurate. And so let me just focus on these calculations done using E plus E minus annihilation data. So as you can see, they disagree quite strongly with the Brookhaven result. Now, this theoretical review was published before the Fermilab result came out. So let's now turn to the Fermilab experiment. So this is an aerial view showing the magnet that was used for the Brookhaven experiment arriving at Fermilab. So the Fermilab experiment uses the same magnet that we saw a few slides back for the previous Brookhaven experiment. And it was then transported by barge and by truck to Fermilab. And it was then installed at Fermilab. And I've shown you pictures of previous experimental teams. So here is at least some members of the Fermilab experimental team inside the magnet. And well, the previous experimental teams were still older white guys. Here, there's a little bit of diversity. So it looks like an Asian lady over here. A few more women dotted around. Still not as diverse an experimental team as one would like. Anyway, that's by the way. So that was shortly after the magnet arrived at Fermilab. And then subsequently, the space in the center of the magnet was filled up with electronic detectors. So the Fermilab experiment, although it uses the same magnet as the Brookhaven experiment, uses a completely new set of electron detectors. So here are some of their measurements. So again, you see this wave-like pattern, which corresponds to the precession of the muon and then the variation in the intensity of the electrons produced by the muon decays. And here's the result. So the result is shown here by this red point with its uncertainty. And as you can see, this result is totally consistent with the Brookhaven result. Now, at the moment, the uncertainties in the two experiments are kind of similar, but the Brookhaven people have analyzed so far only a small fraction of their data. There's going to be much more data coming along, and we can expect that this error bar will be shrunk significantly in the future. Anyway, for the time being, we can take the average of the Brookhaven and Fermilab results. We get this purple band. Here's the central value. And there is a 4.2 standard deviation discrepancy between the standard model calculation and the experimental value. Now, in particle physics, if we're going to claim a discovery, then we typically want to see an effect which is at the level of 5 standard deviations. So far, the experimental discrepancy is not at that level. It's a level of 4.2 standard deviations. But it's very promising, and it has triggered a lot of theoretical as well as experimental interest. So I noticed that somebody asked a question about whether this could be connected to dark matter. I would say that's quite possible. So perhaps you could just hold on to that question for a few more minutes, and I'll show you what I mean. So as soon as the result came out, there was an enormous cascade of theoretical papers. And for the first month or so, I tried to keep track of who was proposing what interpretation of the Fermilab result. But after a month, I gave up. Anyway, these are color-coded according to the type of theoretical explanation that was proposed. And in particular, in green, I've put the theoretical interpretations based on supersymmetry. And if you look at the supersymmetric interpretations, and also some of the other ones, you see DM. That means that people thought that their interpretation of the new experimental result also had a bearing on the nature of dark matter. And that's in particular the case for most of the supersymmetric interpretations. Okay, so let me just show you the very simple diagrams that you calculate in a supersymmetric theory to evaluate the contribution to the anomalous magnetic moment. So these are the lowest order diagrams. So here you've got a muon, you've got a supersymmetric partner of the muon, and this thing here, chi, is what we call a neutralino. It's like a neutrino, but heavier. And one of those neutralinos could be the dark matter. Now, see, what happens in supersymmetry is that, in some sense, the electric charge of the muon is spread out because the muon splits into a neutralino and a supersymmetric partner of the muon. And so that's precisely why, in a theory like supersymmetry, you can get a contribution to the anomalous magnetic moment. Now, that's going to depend on the mass of this muon, the mass of the neutralino. Actually, it's more complicated because there's 2 types of muon or 4 types of neutralino. But anyway, the neutralino mass and the muon mass affect the magnitude of the supersymmetric contribution to the anomalous magnetic moment. Now, if you want to get a big contribution, you need relatively low mass neutralino and muon. And that point is brought out on this slide here, which is taken from a paper that we wrote a few years ago. So here, we're assuming that the dark matter is made up of those supersymmetric neutralino particles. And we find that we can explain the anomalous magnetic moment of the muon if that neutralino weighs a few hundred GeV, let's say less than 500 GeV. Simultaneously, the muon should be relatively light, also less than about 500 GeV. So, in answer to your question, yes, dark matter is very closely related to the anomalous magnetic moment of the muon. And I would say that if the supersymmetric interpretation is correct, then we would expect that there would be a supersymmetric dark matter particle and a muon weighing just a few hundred GeV. Now, of course, you have to worry about the experimental limits on supersymmetry coming from the LHC, which I discussed in one of my previous lectures. And people often tell you, oh, well, the LHC tells you that supersymmetric particles must be very heavy, blah, blah, blah. It's not quite true. There are possibilities, for example, for the muon and the neutralino to weigh 100 GeV or even less. So there's certainly every possibility that the muon and the neutralino could be light enough to make a contribution to the anomalous magnetic moment, and they could very well explain the discrepancy between the data and the standard model calculation. If they do, then the supersymmetric particles would have to be relatively light, and they could very possibly be discovered in future runs of the LHC. And well, I showed you some calculations that I was involved with. Here are some calculations done by other people. And again, those red stars, those are scenarios in which supersymmetry explains G-2 and the dark matter, and also is compatible with the LHC constraints. So I see there's another question. It showed up briefly, yes. Please share my view on the weak contribution to the muon G-2. So thank you, Vivek, for that question. So interestingly, the supersymmetric contribution might be the same magnitude as the weak interaction contribution calculated in the standard model, if the supersymmetric particles weigh just a few hundred GeV. So weak interaction contribution has been calculated at the one loop level. That's a very old calculation. It's also been done at the two loop level. People have also studied the sensitivity of that calculation, for example, to the mass of the Higgs boson. It's very insensitive to the mass of the Higgs boson, but at least people have calculated it. And in fact, when the Brookhaven experiment was conceived, the idea was that they would measure that weak interaction contribution. But maybe they're not measuring the weak interaction contribution alone. Maybe they're also measuring the supersymmetric contribution. So I hope that answers your question. Okay, so that's where we are now. So what's going to happen in the future? So I already mentioned that Fermilab is planning to analyze much more data. And so their experimental error bar will be greatly reduced. And that may already bring the discrepancy to more than 5 standard deviations, depending, of course, on what result they find. Another possibility is a different type of experiment where instead of measuring how electrons and positrons annihilate to form photons, which form hadronic particles, which are what you get when you cut through that egg on the first slide. Instead, you can look at what happens if you scatter a muon off an electron and you exchange a photon between them. And that exchange of that photon depends also on how the photon couples to other particles, including, for example, Steiner model particles, but also including supersymmetric particles. And so there's an experiment proposed at CERN to measure very accurately the scattering of muons off electrons and measure the properties of this intermediate photon. And they're still at the test stage, but if those tests are successful, then this will be an alternative way of making experimental measurements that would bear on this discrepancy. Also, there is an experiment being prepared at the J-PARC laboratory in Japan, which is a sort of traditional type experiment where you capture muons and then you observe them decaying into electrons, and you observe the precession of the muons via the intensity of the electrons. But they don't work at the magic energy which was used at the CERN, Brookhaven, and Fermilab experiments. They use a very low energy muon beam. And so the experiment, instead of being very large, and so you could put your entire collaboration inside the magnet, as you can see in this picture here, the overall size of the experiment is not much larger than a person. So what's going to happen in the future with the anomalous magnetic moment of the muon. Now, I don't think we should forget that there's been tremendous effort in the theoretical calculations. And the agreement between the theory and experiment is actually a tremendous success. There is a discrepancy, but it's a very small discrepancy. I think anybody would be very happy if they got a result which was as accurate as the results for both theory and experiment. However, there is a small discrepancy, and this could be a window on new physics beyond the standard model. Now, there's still some debate about the calculation in the standard model, which I haven't really gone into. But, I think it's a very intriguing situation. There's plenty of theoretical interpretations of the experimental result proposed. For example, supersymmetry, which I mentioned, and there's many possible connections to other physics areas, such as, for example, dark matter, as we discussed earlier on. And there are plenty of new experimental results on the way. Fermilab is going to produce more data. There's another experiment in Japan. There's a Muon experiment proposed at CERN and so on. So I think this is a very interesting time. The anomalous magnetic moment of the Muon may indeed be anomalous, and that would be very exciting. So I finish with this summary slide. So here we have the standard model, beautiful, just like the Titanic ship. But the Titanic ship sank when it hit the iceberg, and maybe the standard model is going to sink because of G-2. Thank you.
Thank you, sir, for your wonderful and exciting lecture, sir. So we have got few questions, but I think you have already answered some of them. So there is another question. Sir, do you think the stereo neutrino contribution is a relevant point in Muon G2 experiment?
Well, I don't think the sterile neutrino per se is terribly relevant, because in order to get a big effect, you need to have a diagram, a quantum diagram, which just involves one loop. And by definition, there isn't a sterile neutrino contribution appearing at one loop. Of course, many of these theoretical interpretations that I discussed are sufficiently complicated. They do contain sterile neutrinos. So I'm not saying there's no connection between sterile neutrinos and G-2. But I think that the sterile neutrino per se is not going to be contributing directly.
Okay, sir, thank you. We have another question. This may be the last question. So do neutrinos have magnetic moment?
So that depends on your theory of neutrinos, but in principle, it's possible. And in particular, if neutrinos are described by the Dirac equation, then that's certainly possible. And there's some debate as to whether neutrinos are described by the Dirac equation or a rival equation due to Majorana. So, the jury is still out on that. But in principle, yes, they could have a magnetic mode.
Thank you, sir. I'd like to say thanks again on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation again. So I think this is very good opportunity for our students and the viewers to interact with you. And hopefully in near future, we can arrange another exciting webinar with you, sir. So, sir, please stay safe and please share your knowledge with us and keep safe from the coronavirus. Very nice.
I hope that you and all your colleagues are also free of coronavirus, and I wish you well for the future. And all the best for 2022.
Yeah, sir. Happy New Year, sir.
Okay, bye.
Bye.